So, thanks for coming. Thanks for getting up after yesterday's party. Welcome to my talk, Keeping Track of Stateful Infrastructure, an overview over the infrastructure at InnoGames and the tools we built to run it. Depending on who you ask, I'm Space or I'm Patrick. I'm a sysadmin at InnoGames. I used to be the primary system administrator for the game The West, and now I do mainly infrastructure software development for InnoGames. InnoGames, if you don't know it, is a mobile and browser-based game company with more than 200 million registered players from Hamburg in Germany. And at InnoGames, we host our games using thousands of VMs with only like a dozen or so of them not hosted on our own infrastructure. In this talk, I want to talk about how we do that without AWS or OpenStack or any of the tools you probably use for that. The primary tool I want to talk about is ServerAdmin, which is a configuration management database we have written ourselves to manage all of it. The reason why we have written ServerAdmin mainly is historical, because back when we have written ServerAdmin, there just was no OpenStack, there was no Netbox. So we have come up with something ourselves. I've checked our configuration management database on Wednesday, and on that day we had on the API 1.7 million API requests on that day, just reading. We had 37,000 API requests writing to this configuration management database, and that's just one day. We also have like 158 types of attributes and 42 types of objects. So those are like different concepts like a virtual machine or a hypervisor or a load balancer. And we had 21,000 objects, which can be either real machines or some kind of configuration information. And with this talk and with these numbers, I want to challenge what your expectation of what a CMDB should be. Right. These are some of the systems that all hook into ServerAdmin for us. We have integrations from our own custom virtual machine orchestration software, from Puppet, in our networking, backupping, DNS, everything's integrated. And in this talk particularly, I want to talk about some of those integrations, which are our virtual machine orchestration, our configuration management, and how we integrate Puppet into ServerAdmin, how we load balance traffic which comes from the internet to all our servers, and about how we do DNS internally at least. Let's start with the virtual machine orchestration example. Imagine building your own virtual machine orchestration software, like something like OpenStack maybe, using just Netbox or Rack tables as your database backend, where you just store all your state you have in there. I think you will have a hard time. And my reasoning behind this is you will have mostly problems with the very rigid schemas those software provide. Netbox comes with they have an example of what a data center is, what a rack is, what a hypervisor is, and so on. But when that schema doesn't fit your reality, you have a hard time changing it. For example, in my last job, I subscribed to some GitHub issues which just recently got resolved, which I'm very happy about because I really like Netbox. But for example, this one is about tracking different types of cabling in Netbox, which took like, how long? 2.5 years to resolve. And they came up with a really cool solution where you have like all kinds of cables which can end in different types and really complicated stuff that can cover mostly anything now. But if you need a solution now, you don't want to wait 2.5 years. And one example which is closer to what I want to talk about, they didn't have virtual machines when I used Netbox. The basic solution was always like, yeah, just take like a blade center and make them blades or whatever. And that's not really good. ServerAdmin is more like another normal database, like an SQL database, which doesn't come with the schema itself, at least not with a lot of schema. It requires you to create one yourself. The first type of thing you have to care about are attributes. Attributes in ServerAdmin, you can kind of imagine like columns in an SQL table, or you can imagine them like class attributes in object-oriented programming. So you first go ahead and create some attributes. Here, for example, I want to create an attribute CPU model, which makes sense for hypervisor but not for virtual machine. And I want to create an attribute called game market, which makes sense for virtual machine but not for hypervisor because we don't couple those. When you create an attribute, you first have to give it a name, always. That has to be unique, of course. You have to give it a regular expression to check the validity of values this attribute can have. You have to give it a type. And this is also a really cool thing in server admin. All the attributes you have are type checked. So there are certain basic data types like strings and numbers and booleans and dates which are fairly straightforward and they do exactly what you imagine. But there are also some specific data types which are particularly helpful for a configuration management database. Like we have ENET, which can hold IPv4 and IPv6 host addresses and networks. We have MAC address, which can hold MAC addresses. We have relations and reverse relations I will show you later. And we have some even more special data types which are relational, like SuperNet. So you can say something like, okay, this host has an IP. I want to get the next bigger network that includes this IP. Right, so those are the main things you have to care about for an attribute. Other than that, there's also a read-only flag you can set. There is a flag you can set if an attribute can have multiple values. Right. The next thing you will care about are server types or object types. For example, here I've created the server type hypervisor and the server type VM. You can think of them like tables in SQL or classes in object-oriented programming. Again, when you create a server type, you first have to give it a name, and you have to attach a list of the formerly created attributes to it. So one server type can have a certain set of attributes. And for each of the attributes you add, you can set some more flags, like, is this attribute required for this server type? What's the default value of this attribute for the server type? And there are some more special ones I will not go into too deeply. Also, you can give the server type, you can tell what the IP type of this server is. So you can say either this is a host, or this is a network, or something else, like it doesn't just, IP addresses do not apply. Of course, one attribute can also be attached to multiple server types. I mentioned relations before. So you can have an attribute which is of type relation and has a certain destination server type. So it will, for example, the server type, the attribute hypervisor will always refer to a server type hypervisor. And you can also reverse relations you have previously created. For example, you can have an attribute called VMs on a hypervisor, which is pointing to this relation from VM. So you only go to your VMs and define the hypervisor they're running on, and the hypervisor gets the reverse information for free. So you can ask what VMs run at this hypervisor. Right. This, of course, means that the reverse relations are always one-to-many relations, basically. Using the schema we have just come up with, we could have some objects in our database using this schema. So we create a hypervisor object. And this hypervisor object can then have a certain server type, which is an attribute. It can have a host name, the CPU model we previously defined, and it can have VMs, which is actually not writable on this side because it is a reverse relation. It is only writable on the right side, on the VM object. And the VM object then can have a server type, a host name, the game market we have previously seen, and it can set the hypervisor. If you've ever worked with EAV or entity attribute value databases before, that should look familiar because this is what server admin is at its core. The full name would be entity attribute value with classes and relations. Though it's good to note that our naming is kind of off. We call attributes attributes and values values and relations relations, but the entities we call either servers or objects, and the classes we either call server types or object types. given this schema and data in server admin, you now need to be able to actually create and query and delete stuff in server admin. And for this, we have 3 easy ways plus an API, basically. The first thing is we provide a Python library, which is the most straightforward thing you can do. Then we have a command line utility using this Python library. We have a web interface for manual mass editing of different kinds of objects. And you can use the API directly, of course. So this is an easy example of creating an object in server admin. Whenever we interact with server admin, we basically first import this query class. This query class, then in this example, we want to create a new object, so we call the new object function and tell it the server type. And this will go to the server. It will check out the schema information on the server and get back a dictionary of what such a server would look like. So which attribute does this server have and what default values does it have. And we save this in an object in Python here, and then we can update the information and override simple things with passing another dictionary. But only when we call commit on it, it is actually saved to the database. So we have create. Now we do reading. Reading is straightforward, so you also take this query class, and this query class usually takes 3 arguments in its constructor. The first one is a filter, and the filter works in this way that you have a dictionary with the key you want to, the key being the attribute you want to filter on, the name, and the value being the value you want to match. If you just give it a direct value, this will be an exact match. If you give it an extra filter like I've done here with any, you will get certain extra filter things. I will show some other filters down the road, but just know that there are different filters available. All these attributes, or all these filters in this dictionary will be ANDed. So your servers, the servers that will match this query will have to match all of these, so both. And further, this will only consider server types which even have these attributes. For example, a hypervisor will not have game market, so it will never match this. The second list we pass to it are the attributes we want to get back from the servers that matched. So here we ask for hostname and hypervisor. The result could be something like here on the bottom where we see, okay, we have the hostname we asked for, we have the hypervisor we asked for. It is only one object because only one matched in this query. And it's also good to know that we get object ID back, which we will always get back when using this Python library. Object ID is basically the primary key on the entity table in the database behind it. So even when you change the hostname, we will always keep the same object ID. Making this a little bit more difficult, we can do joins in our query too. So check out how we here requested hostname and hypervisor, and here we still request hostname and hypervisor, but hypervisor is now in its own dictionary, again with a list of attributes behind it. So we basically join all matched servers on their hypervisor attribute, and from that hypervisor again get hostname and project. And in the result you can see we still get the same server back, but the hypervisor attribute no longer matches to AW, HV, whatever, but it matches to a new dataset object with its own attributes in there. Now let's look at updating. When you want to update, you do the same thing. You take a query. Before, I was always directly passing it to lists, so we get the output of what is actually on the server. Here, I'm saving the query in the queue variable. And I can iterate over this queue variable and change all the objects that were matching this query. And all these changes will only be locally in my Python until I call commit on the query. Again, here it is good to note that before we were committing the server, now we are committing the query. Both is possible. You can either say, I want to change something on the server and commit this right away, or you can say, I want to make a very complicated change on many objects and then commit the whole thing. And it will be committed in one SQL transaction. It will make sure that it is consistent throughout. Also, committing this will, of course, make sure that what you are committing makes sense, that it will make sure that it makes sense. It will make sure that you are allowed to change it. So we don't have ACLs currently on reading. So if you're a user in the system, you can read everything. But we do have ACLs on writing. So we will make sure that you are allowed to change this kind of server and you're allowed to change this attribute on this kind of server. Further, there's one more safeguard here, which is there's some time between us retrieving the information, changing it, and then committing it. And server admin will always send back what, the admin API, the library, will always send back the old and the new value it expects. And when the old value doesn't, while committing, the old value doesn't match what server admin now has in the database anymore, it will tell you, your data is stale, please recommit this, it's not safe. So, final example, deleting. Again, we make a query. Here I show you the get function you can call on a query. The get function basically makes sure there's only one server matching your query, gets back this server. Otherwise it will raise an exception if there's 0 or more. We delete it. Again, deleting it doesn't really commit it. We need to commit it then. That was the first and most used way, I would say, for interacting with server admin on our side. The second one is the CLI client. So you can do most of the same things. You can say admin API, you give it some filter. Here I filter for one exact host name. Then you can give it -a attribute name for every attribute you want to get back. Here I'm asking for the hypervisor. And having this on the command line is kind of neat because you can directly, for example, pass this output to SSH and then you have an SSH shell on the hypervisor where this VM is running. Another neat tool I want to show you really quick is polysh, which is not a tool we haven't written but we maintain now. And polysh is kind of cool because here we can, I made a query where I said hypervisor equals some specific hypervisor, and this is the textual representation of this query dictionary we have seen before. So instead of having a dictionary now, we just say attribute name equals the value. And you also can use filters in here, which you will see in a moment. We get back 3 servers. We can take this output and stuck it directly in polysh, and we will get one prompt where we can get information from all these 3 servers at once. Right. So here I'm showing you what it looks like when you filter for multiple. Of course, you now have to make it a string because it is space separated, the attributes you're filtering on. You can see that I'm using the regex again, and it looks like this if you want to use it. Also, in this example, I'm getting back 2 attributes. I'm getting back hostname and hypervisor, and this is what the output would look like. Doing one more example with like all the complex thing you can throw at it. You have a query. You have attributes you want to get back, hostname and state. You have an -o, which means order by, and you again give it an attribute you want to order on. In this example, I'm using object ID because since object ID is the primary key and auto increment field, it will automatically order it by creation date this way, basically. And the last thing I'm doing is -u for update, and I'm setting one attribute to a new state. And you can see it in the output even that it's now maintenance. Yeah, this is basically what the CLI tool can do. And the last thing I want to show you is server shell, which is the web interface we provide with server admin. It comes with server admin. You get two inputs here, basically. You get first search. In search, you can put the same textual representation of a query we have previously seen in the command line utility. Once you hit enter there, you get all the servers back immediately matching your query, and you will get shown some attributes right away. For example, hostname and internal IP, server type, some very basic things. One thing to note here is that this is called internal IP. This will be important in the talk. Ignore this. Imagine this says primary IP or something. It is not intern at all. The second thing you have is the command field. In this command field, you can literally type different commands. That's why it's called a shell. One of the commands, for example, is attr. You can say attr and attribute name, and this will toggle the visibility of the attribute I'm typing in. Server type is already visible, so when I hit return now, this attribute will go away. The second thing I want to show is we are currently matching 2 servers here. In reality, it is totally normal that you are matching hundreds of servers you are working on. So you want to be able to select different ones of them. You have commands in Server Shell to edit them. There is a command to delete the value of an attribute, to set the value of an attribute, to add another value to a multi-attribute field, so a value which can have an attribute which can have multiple values, and to delete things from a multi-attribute field. But if you type them, Server Shell will just tell you, please select some servers first. Because in opposite to the command line utility, this will not just change all servers matching, but you actually have to select the servers you want to change. Default, none is selected. When I type 1 here now and I hit return, see that the checkbox gets checked. And there's, like, you can either type the numbers or you can say select all, that's also possible, or unselect all. Right, so now we have 1 server selected we actually want to work on. Now I can use the del attribute command with some command name, which will mark the subproject as to be deleted. Again, it's not committed yet. It is only noted for deletion. Another one of these commands would be delete. Note that I toggled the selected server, so now I selected the second server, not the first one anymore. When I hit enter now, the second server is marked for deletion completely. But only once I now type commit and return on this, the server is really gone and the attribute subproject is really cleared. Again, in a single transaction. So another cool command is history. We keep the history of all attributes of all servers which were changed. We have just changed of this first server, the subproject one. So when we check the history now, we can see that this attribute was actually set to no value at what time by whom. And that's really, really helpful too to understand what happened here. Also, as I said, there is this multi-attribute fields, and just like we used del attribute before, we can use multi-add to add a second value to this field. And the last command I want to show you is graph. Graph is part of our Graphite integration into server admin. There's different ways to get Graphite data into server admin, but the one I want to show here is that you can define you can basically define a board of queries you want to see for a server. This is just one of the dozens and dozens of things you will see because I made it so big. But for example, when you select 10 servers and say graph, you will get from 10 servers their load and immediately get it in the server admin interface, which is also really neat. So finally, let's move on to IGVM. IGVM is our VM orchestration tool. The way it works is it goes ahead and queries for the server you give it, for example here, VM host, host name. It will also query the hypervisor if one is set. If you didn't set a hypervisor for your VM, it will just query all hypervisors available. If you didn't set one, it will then elect a hypervisor which makes sense for this hypervisor when you are building it, based on is it loaded, is it even available in the network you want, and so on. It will go ahead and lock both the hypervisor and the VM you're working on. Again, it does the locking simply via an attribute called IGVM locked in server admin, which is available on VMs and hypervisors. So we'll just set it to true. And further, while it doesn't create objects in server admin, you have to create it first. It updates them. So when I use disk set and increase the disk size, it will increase the disk size on the hypervisor, but it will also increase the disk size noted in server admin. And of course, this is a command line utility I'm showing here. But again, this really is just a Python library which we have wrapped the command line utility around. So you can use all of these things in just like you did with, like I showed with the Python admin API example. So let's kick off a demo in the meantime really quick because it will take some minutes. This is not very bright. Anyway, I'm just running some script here I will show you. This feedback is bad. And my network is gone. Well, no demo, I guess. Yep, no demo, sorry. Maybe I'll show it later. So I wanted to show how I built something with this thing actually, but it takes like 2 or 3 minutes, so I wanted to start it now. Then let's move along. The next thing I wanted to show is how we integrate Puppet into Server Admin. I won't go too much into how we use Puppet in general, but I just wanted to show the points where we retrieve and put information from into Server Admin in our Puppet setup. The most straightforward way we do it is, again, we basically re-implemented a tiny version of Admin API in Ruby to use in here. And for example, here you can see that we do a query 1 to get one attribute of a server matching. We can give it the same kind of attribute-based dictionary to filter on. And we get back the database address here. And this is a very easy way to just say, for this game market, for this world, for this function, I want to get an IP, and then I can immediately put it into my configuration on my web server, for example. The same way there's a bit more complicated the normal query one, which behaves even more like the Python version, where you give it multiple attributes, and you get a list of dictionaries back, or hashes or whatever it is in Ruby. And you can use it just like any other Puppet data object, and you can call reduce on it. And here I basically flatten the list of available projects and project networks, and just get all the project networks in this project and their IPv4 and IPv6 part in a flattened list. So this is very much the same as we had in Python. One thing we have in Puppet explicitly is we built our own Hira backend. So who here knows Hira? Please raise your hands. Okay, and I will explain it really quickly. So in Puppet, you create these classes, and classes can have attributes. When you include classes, you can set these attributes if you want to. And a lot of how you abstract the way Puppet to work in a way on multiple machines is that you create these classes with these parameters, and then you create Hira files, which are usually JSON or YAML files, basically by exact hostname or by some other, like maybe you say production and staging and then exact hostname. They're included in this order, and then you can set these variables from there, which then can make them behave differently. And instead of writing, additionally to this opportunity to write YAML and JSON files, we have also invented our own Hira backend for server admin. So when Puppet runs on our servers, it first goes ahead and makes this really gigantic request to server admin for a couple hundred attributes for the server that's running on. And it's like asking for its network configuration, its load balancing configuration, and this is just like a very small subset of things we actually query. It's much more. And when the answer is returned, it is like normal Hira, just stuck to this class specifically. And then you can access all this information from server admin during the run via calling $IG : server : and then any of the names here, for example, intern IP, and then I can just use it. The last example I want to show you is NAPE command. NAPE command is a custom resource type we have invented for us, which we use to define Nagios checks. So we have a lot of shared Puppet code between projects. For example, we have this gigantic set of code for setting up different things in Postgres. And all over the place we are using this custom resource type to define checks. And since it is in the shared code, I can just include it. And like the name suggests, this basically is where the source for our Nagios checks comes from. It does two things. First, it changes the NIPE commands config on the local machine we are on. But secondly, which is more interesting, it uses this change multi-attribute function to add a value to the object. So here we see we have IG server object ID. This comes from the hero I explained before. Then we have an attribute name called monitoring checks, which is the attribute we are changing. And then we are adding a check. For example, this will be the check name when I call this class with, like this, for example. I call it with the name CPU steal time, and I give it some command path. CPU steal time will automatically be added to the monitoring checks attribute of this server. And this is really useful because then I can just go ahead and run Puppet on our Nagios server again, and the checks will immediately be there. And since we have these things all over the place in our shared code, we basically just I do 3 lines of including Puppet code, and then I get a Postgres running plus 20 checks for the Postgres already there. And here I just used admin API to show that it will show up on this attribute basically, but whatever. The next thing I want to talk about is how we load balance incoming traffic to our servers. So we have requests coming in from the internet basically, and they will always hit a load balancer at InnoGames. The traffic is routed to our hardware load balancers via BGP, so they announce certain networks to upstream routers. Which networks are there and which servers are behind those IP addresses is again coming from server admin. The incoming traffic is then load balanced to the available nodes via a PF firewall. So we go ahead and we have this tool called test tool. It is running on every hardware load balancer. What it does is it gets the configuration from server admin. It does health checks on all the nodes. So I have game web server IP. I want 5 nodes behind. It will check, is every node healthy? And if it is healthy, it will insert rules into our PF firewall on FreeBSD to forward packets to this host. The next thing to know is that all app servers serving a public IP have that IP attached to their loopback interface. And this is really useful because this means that load balancers don't have to touch the IP packet at all, basically. The load balancers get the IP packet in, and they just have to resend an Ethernet frame to one of the application servers which feels responsible for this IP. And that makes it very cheap to do. I would call this direct server return light, because that's kind of how we do the way to the server. But usually you would do something like this, where you directly return from the application servers to your upstream router. So you have async. So with load balancers, you can make this neat setup where you have asymmetric routing, basically, where you go in through one way, but you can go back from the application servers to the internet directly. And this allows you to have a bigger backward bandwidth, basically. You can see we can send more replies because it doesn't have to go through the load balancers again. If you would run a CDN, you would probably run it like this. But we don't. We use outside CDNs, but we really like the opportunity to firewall outgoing internet traffic from the application servers. And this is why we route our traffic back through the hardware load balancers. But this is just a configuration change. Basically, you can change this by just changing the default route on the application servers. Test tool is a direct server return tool. We think this is useful for the kind of application server we are running. Test tool and our FreeBSD patches to make this work are also completely available on our GitHub. So the configuration we might have for what I just showed you is usually looking like this. So we have this load balancer server type, which is a completely virtual concept. A load balancer also has an internal IP, again, read primary IP. and protocol ports which say which ports you actually want to forward to the application nodes. A VM then has a relation like it did with hypervisor, but now it has one with load balancer. And it can say, I want to run behind this public IP here. And then the final thing is the load balancer has a relation to health check, and health check is a server type which just defines how to check if a server is healthy, which can, that's different for a web server than for a database server. Checking some examples. This is the easiest one for web servers, for example. So we have a server type load balancer. It has a public IP. It wants to give port 443 and port 80 TCP to the nodes, and it has a health check defined. Checking the health check on the right, we can set via the attribute HC type on the health check server type. We can say this is a health check for HTTPS. HC port says the service we want to check for the health check is running on port 443. And the query we want to make is a HEAD request to this specific URL, which is like the backend can then decide what it wants to do. It can check Redis, can check the database connection or whatever. And if it doesn't return the correct return code, which for example here would be 242, it will be considered not healthy and not receive traffic anymore. The second example I want to show you is database load balancers, which basically the same deal. You give it an IP, here it is an internal IP. You give it a port. For example, I'm using 5432 default port for Postgres. I'm defining a health check again. And this health check is interesting because HC type now is not HTTPS anymore, it is Postgres. And this means it will open a Postgres connection to port 5432. It will authenticate, and it will run some select there to see if this node is healthy. And this particular select here is querying a stored function we have defined ourselves via Puppet on the databases. And basically, in the backend, it checks some things like, it checks the replication state. Do I have replication lag? Do I have nodes following me? Am I the replication master in our replication setup? And only if it is, like you can put 3 databases in it, and only the master will ever be considered healthy, and only this 1 out of 3, for example, would then be in the load balancer. But the web servers don't have to care who's master. They will just connect to this IP and they will be fine. They will always reach the master. Okay, and the final example I want to show you is our PowerDNS setup. PowerDNS, usually when you set it up, it comes with, their Postgres backend comes with a schema kind of looking like this. It does many more things, but the primary table here is the records table defining some information interesting for a DNS record. And we thought that looks interesting. We can kind of build something like this on top of the existing Postgres data. So server admin uses the Postgres database in the backend. And for example, here you can see that we have this table called server. This table has attribute hostname, attribute internal IP, and we check if internal IP is not null. And if all of this is true, we just create a view, select it in this view, and you can transparently use PowerDNS. PowerDNS thinks it has its own database, but really it's just a view on top of server admin. So when I commit an object to server admin, it is immediately available in PowerDNS. And we can, since we already have this records view, we can put even more cool things in there. For example, we have this attribute called SSHFP, which is an attribute which is populated by IGVM when a VM is first built. So we build a VM, we note down the SSH fingerprint for this server, and put it to some server admin attribute via Puppet or maybe even via the API directly, I'm not sure. And since this information is available, we can expose it here as an SSHFP record type in DNS. And since we also have DNSSEC, this allows us to then transparently check if when I connect to some new server I've never connected to before. Usually in SSH you get this, well, this is the fingerprint, do you accept, yes, no. And we just have disabled this on our server. So it will no longer ask. It will get the fingerprint. It will check against DNS if it is fine. If it is fine, it will connect and not ask you anything. If it's not fine, it will not even ask you. It will just deny and say this is unsecure, I cannot connect. So I think that's all I have. Thank you.
One second. Yes. Hello?
Nope. I think you killed it.
This one? This one? This one? Yes. Please wait with moving out until we're finished with the questions. We have a couple of 5 minutes or so for questions. Does anybody have any questions? I have a question. I really liked your stuff. The question I had was about the workflow. So you have the server admin as a tool?
Yes.
And then, so when would you be using these things? Because you're going to put you're going to change the server in like the CMDB, and then do the changes on the server, or does like Puppet automatically update the CMDB?
Right. So certain things, like I mentioned, monitoring checks would go from Puppet to server admin. But usually the workflow is that server admin describes the state you want to have. So you first say, I create a load balancer, I create a VM, and then I build the VM, and then it is just the state that is defined there. So it's how I want it state, usually.
Thank you very much. There's a question here. Let me get some exercise.
Hello, I'm Thomas. I maintain OpenStack in Debian, and maybe I'm too much oriented.
Sorry, I cannot hear it.
Okay. So I maintain OpenStack in Debian since it existed, and when I look at your presentation, it looks like to me that you are reinventing it. All what you have there seems to be already in OpenStack. So what made you restart from scratch? And did you look into OpenStack, into Octavia for load balancing, into Designate for DNS as a service, and so on?
This stuff is older than OpenStack. We have recent, it has been, most of these tools have been released in like the last 2 years or something. They're all on GitHub now. But this all started either when those tools were very young and not really mature at the point we needed them, or where they just didn't exist. But I still think I don't think we have a big interest in changing away from them because we have big in-house knowledge about how they work. Like when getting into OpenStack is really like getting your feet wet with that, and like really not only getting a VM running, but knowing what to do when crap hits the fan. That's really difficult, and we really know what to do here and what we are doing. It's like very modular system we have built here.
Fair enough. Any other questions? I see 0 hands. Okay, thank you very much. Good job.
Thank you.